Tools, and we're going to be going over gauging your performance, which is part 3 of a 4-part seminar we've been doing. Today should be really good for a lot of you guys and gals out there. There's quite a bit to go over. I'm going to try and take some time here and make sure everybody understands this when we're all done. If you do have questions, please feel free to type them into the question box, and we'll try and answer them as we go along. Sometimes if it seems like I'm ignoring it, it's just because it's coming up. So these really will stand on their own. We are going to be recording the other. I think we missed one of the webinars recording it, the first one, and we will be going back and re-recording it and posting it up on our YouTube channel if somebody wants to see that one. So, but we're going to go ahead and get started. And if you have any questions to go, again, please feel free to chime in. And so let's go ahead. All right. So just to start a little bit, if you're in the first 2 seminars, it's a little bit of review, but I just want to make sure that as a group, everybody understands what's going on here. And as an industry, there's been several studies that have gone on. Oops, let me see here. Show my screen. All right. Okay, sorry about that. I didn't have the screen up. All right, there's been several studies that have gone on through Energy Star to basically quantify the problems within our industry. And what they're looking at initially, this was a 2006 study that was done, is if a system's not set up correctly, what was the impact on operation, and would you want to still stick the Energy Star label on a piece of equipment that may not be commissioned properly, because there would be energy losses that they didn't anticipate. So there's a lot of studies done in California and across the country, really, that looked at airflow and charge, and this is just some of the data from these studies. But what they found out is that refrigerant charge is basically essential to maintain capacity. And if we had improper charge, it was going to lead into premature compressor failure. In the studies, they found 41% of systems were undercharged and 33% overcharged, and that there was an average savings of about 12.5% with proper charge. And that charge had to be adjusted by the technician in accordance with manufacturer's instructions. And what they found out, and this is just something to keep in the back of your mind because we're going to talk about this later, was that systems with more than a 3-degree deviation in subcooling, we're talking about high-efficiency TXV systems now, would not qualify for the Energy Star rating. That was one of the big things that went through this. Now this study was about Energy Star, and this part of it never went through. But what I want you to catch on this is that a 3-degree deviation in subcooling would not qualify for the Energy Star label. What the key thing to remember from this is 74% of systems have improper charge, right? That's what the study found, and that in itself says that we have huge problems. California PUC did an analysis of 13,000 residential and commercial units. They found most were off half to 5 pounds of refrigerant. AC units that were off by more than 8 ounces would potentially fail within 5 years. That was have a failure. So compressor failure, contactor failure, they could short cycle, they could, due to a high pressure switch or a low pressure switch, but they have some kind of a failure within 5 years. In the cap tube systems or short orifice systems, even an ounce or 2 refrigerant would have a serious impact on performance, and they found almost exactly the same thing. 74% of units were incorrectly charged. The causes of this were improperly calibrated measurement equipment and human errors during commissioning. When we look at charge just as part of the installation, okay, and we're looking at a 15-SEER system right here at the peak of the graph. Let me just pull out a felt tip pen here. So what we're looking at is at the very top of this graph right here, if we got 15 SEER out of a 15 SEER piece of equipment, it would be sized right, we'd have airtight ducts, we'd have correct airflow, and we'd have correct charge. And you can see here that correct charge picks up about 1.5 SEER of performance on a piece of equipment. So we're looking at this section of the graph right here. And so correct charge has a very large impact on operation of the equipment. Shut that pen off. When we commission the system, to get the correct charge, we got to do a few things. Number one, we got to set the airflow. We got to ID the metering device. We have to know what type of metering device we have. We're going to charge it by superheat or subcooling, and then we're going to check split across the evaporator, and I'll cover that in some more detail. Then we want to document the operation. In order for the system to work correctly, okay, all the systems must be listed in the ARI directory, and that means more or less, if they're not listed, they really don't have. They may work, they may cool a home down. You're going to get some kind of performance, but you're not going to get any kind of a guaranteed performance or documented performance out of the system. When you get a mismatched system, it's very hard to determine how much cooling that system will actually do, especially when we have like a 2.5-ton evaporator coil and a 2-ton condenser. There's a limiting factor in there, which is typically the 2-ton condenser. You're going to change the latent sensible split. In other words, the amount of heat to humidity we're going to remove. So we really need to make sure the system's matched when it's installed if we're going to get the guaranteed energy efficiency, capacity, and reliability that we're trying to sell the consumer. And because a few ounces of refrigerant charge changes everything, these systems become a little bit trickier to charge correctly because you have to be very careful, and you have to make sure that we have correct metering devices and other things. Otherwise, the system may not work properly at all. When we're talking about airflows are critical to proper operation of a system because airflow directly affects the efficiency, capacity, and creature comfort. We're talking about, airflow impacts humidity removal, and if we don't get the proper humidity removal, we get a home that's cold and clammy. Proper airflow across the evaporator is also critical to achieve the efficiency ratings. If we don't have enough airflow across the evaporator, we're going to have low output of the equipment. So we want to make sure that we do that. And I always get the question, do you size the, when you're setting the airflow, do you set the airflow to the evaporator size or the condenser size? And you always set it to the condenser size, okay? Because in this case, the condenser is going to be the limiting factor, that 2-ton condenser on that 2.5-ton system. And you never want to undersize an evaporator coil. If you undersize the coil, you're going to freeze it up. Typically, manufacturers will list a matched evaporator size coil, 2-ton, 2-ton, and then they'll list a 2 and a 2.5-ton, 2-ton condenser, 2.5-ton coil. But you won't see a 2 with a 1.5-ton coil because that causes operational problems. So if you undersize the evaporator coil, you're going to have a whole slew of other issues you don't want to deal with. We talk about setting airflows. We're talking about nominal airflows. So typically we're talking 400 CFM per ton, and this is just a chart of 12,000 BTUs, 400 CFM, 1,800, 600, all the way down the line. And if we were going over 5 tons, obviously this ratio stays the same. Some manufacturers do have systems that operate at less than 400 CFM a ton. Carrier makes a system that operates as low as 350 CFM per ton. But you'll find out with a lot of those manufacturers it's operating at a lower airflow and it's operating at a lower capacity, or it's a multiple stage compressor. Typically, all manufacturers operate at the same ratings, which is 400 CFM a ton, and that would be your full load or your full speed capacity. When you drop that airflow down, you're going to get better humidity removal, and that's why some of the manufacturers have done this. If you've been in the industry for a long time, what you found out is they're making evaporators larger, and the reason they make the evaporator larger is simply to increase the suction pressure, which decreases the pressure across the compressor. If we raise the suction pressure, we're changing that pressure difference. And so what they're trying to do is by force feeding the compressor to make the system more efficient. But when you raise the pressure, you also raise the temperature, and then we don't dehumidify. So it's sort of a way of working the system to get higher SEER out of the equipment, because we can make the compressor work less when we have a higher suction pressure. But on the other hand, we don't dehumidify as well. So what they're doing is they slow that fan down to 350 CFM per ton to get the humidity removal, so it actually doesn't operate at its optimal efficiency all the time like you'd anticipate it would. We talk about IDing the metering device. Okay, it's critically important when you charge a system that you know what type of metering device you have. And the one on the left is a fixed orifice. And a fixed orifice has got inside that brass nut, you'd see a small piston. I have a picture in a slide coming up. Or on the right, we have a TXV, a thermostatic expansion valve. And a couple things, you look at that TXV, you might notice that bulb, well, number one, notice that the bulb is clamped down. on a thermostatic expansion valve, that bulb has to be clamped down with a copper clamp because it needs a very positive contact with the suction line. And you'll notice that that bulb is an uninsulated bulb. And the reason it's uninsulated is because it is in the airstream of the evaporator. So, the air coming off the evaporator is maybe 50 degrees, and the bulb's probably somewhere around that same temperature. So there's the heat gain in that part of the system to the bulb will be very, very minimal. It'll have very little influence on the bulb temperature. If you were on an exterior mount on the suction line, like the bulb actually came out of the cabinet and outside, we want to make sure that bulb was well insulated so that the ambient air wouldn't have an impact on the reading. So those are just some things when you're looking at these things, we need to know what we have. Now, what I want to get, one of the things that's real important when we talk about charging is, do you need to switch from analog gauges? And I want to cover some stuff on that because the way that the industry is headed today, we need to dispel some myths. We need to make sure you understand exactly what's going on and why we make some recommendations that we do. So I want to spend a few minutes talking about the state of the industry that we're in. And again, 74%, 7 out of 10 systems are incorrectly charged. So, we got to make some changes somewhere, and this is a good place to start. Without need, though, there's nothing but fluff, And so the questions I want to answer: do you really need a digital gauge? Is there anything wrong with the way you've been charging? Are there any benefits aside from the digital display? I get a lot of old timers that say, I can do math in my head. I don't need some calculator to do the math for me. It's a little ridiculous. Well, there's sometimes a little more to it than it looks on the surface. We talked about this already. 7 out of 10 systems suffer from incorrect charge. Are digital gauges expensive? Are they reliable? And are they easy to use? So I want to go over some of the stuff in detail. And let me hit the next slide here. So are there really any problems with analog instruments? And let's just go over the facts first. There's the old school tools of the trade were gauges for each refrigerant. If you remember being in this industry for a while, we had an R12 set of gauges, we had an R22 set of gauges. Now we have an R410A set of gauges. You required 3 sets of gauges. You had a pressure temperature chart you had to carry in your pocket. You had a thermometer that you carried, some kind of a high accuracy thermometer, superheat thermometer, maybe a calculator, pen and a paper to calculate the superheat and the subcooling. This is a very common way of doing things for the last, well, probably close to 100 years now. And although we've been using the same technology for the last century and a half, and albeit today it's more precisely manufactured, these gauges can only produce readings that are okay. And I'll explain that in some detail. Because they were in specification when they left the factory, but only to 323%. And I want to cover what that is. And the question becomes, is close enough good enough? A standard 323 gauge, okay? And this is one of the dangers here, and I'll explain to you. These are just R22, R12 gauges, and you might see gauges out there that are R22 and 410A. A lot of guys are using the analog gauge set. And but here's what I want to show you. A standard gauge, when you look at from 0 all the way up here, if we follow this up to this point right here, okay? So from 0 to 40, that gauge is plus or minus 3%, and that equates to 3.6 psi. So it's plus or minus 3.6 psi, all right? When we get to the center of the span of the gauge, and this is where the gauge is most accurate, so now we're up here at the top here, and that becomes plus or minus 2.4 psi. And then the latter half of the gauge from 90 to 120, which is actually, right here where that's going to stop. Again, we're at plus or minus 3.6 psi. Now, if we're talking 410A gauge, this is the reason we don't want to use this R22 gauge for 410A. It's not just because the higher pressure, but it's because this gauge will not read accurately at the top end of its span. It's designed to operate in the center of its span. We'll get a high side gauge, right where we'd be at the center here of the high side gauge. We're at plus or minus 10 psi. Okay, and that's a brand new perfect gauge right out of the box. A brand new perfect gauge. You'd be in the center of a span where it's most accurate. It's plus or minus 10 psi. Now, if we're outside of that center of its span, we're at plus or minus 15 psi, and that's quite a bit of difference there. So, just keep these numbers in mind for a second. Well, one of the grand things the industry did was they said, you know what, we're going to get away from these 323 gauges. We're going to go to a 1% accuracy gauge. Well, follow this for a second, because 0 to 350 is the span of the gauge, right? 0 to 350. Well, what's 1% of 350? It's 3.5 psi. So we actually, if you go back here for just a second, we're at 2.4 psi. We went to 3.5 psi. We actually lost ground on this 1% accuracy low side gauge. And even though they're 1% accuracy gauges, it still doesn't eliminate the characteristics of a gauge, that it's still at most accurate in the center of its span. So again, if we're using this gauge right here from a typical R22 application, which would typically be somewhere around a 40-degree coil, right? We're not near the center of the span of that gauge. If we're in a 410A application, now we're still at that 40-degree coil. We're right here, and we are at the center of the span of that gauge. So you're still, even though it's a 1% accuracy gauge, you're still not going to be as accurate if you're using that same gauge for an R22 application. If we look at the high side gauge, now we did gain a little room there. 1% of 800 is 8 psi, so we did gain some ground there. So let's look at how that influences operation. Now, before we hit that, I threw this slide in here because I also wanted to show you a couple things here, because obviously at the end of the day, we're only reason we measure pressure is to convert to a temperature, and we're converting to a temperature so we can calculate superheat and subcooling. So if you look at these temperature pressure charts that are out, almost all of them are exactly like this. And you can see here, we go up, if we're looking at this section of the chart right here, it goes up in 1 psi increments, right? So 30, 30, 31, 32, 33, through 40. That's pretty normal. And it's showing you over here the corresponding saturation, the corresponding pressure for that saturation temperature. And so we're dealing with 1 psi increments. Over here, though, when we get over to this side of the equation, if we're calculating subcooling, we're at 100, 105, 110. Look at these pressures, 196 to 210. So we have, 14 pounds of difference here. Well, what's the technician left to do here? Because if you're going to remember, Energy Star told us plus or minus 3 degrees. Well, if I've got a gauge that's plus or minus 8 to 10 pounds, and I've got a temperature pressure chart where I've got to take a guess or interpolate where that lands, it's not a whole heck of a lot of chance of me ever getting that getting that subcooling within 3 degrees that the manufacturers are requiring. So it becomes a challenge, and this is one of the big reasons that systems aren't charged properly. When you talk about measurement accuracy, it's really important that you understand that every measurement has a target and it has some measurement uncertainty. Okay, and what that means is, in this case, we say that we're plus or minus 5 degrees, and that's our target, right? And a lot of guys, if you've charged a system up before, you use the charging chart, it says, okay, you got to be within plus or minus 5 degrees. And I don't care whether you're talking superheat, subcooling, a wet bulb temperature, dry bulb temperature, a line temperature, any measurement you make, you got to look at the accuracy of the equipment you're using, and you got to look at the target. How accurate do you want to be? If you're going to be plus or minus a half a degree in temperature, you're going to require a very, very expensive thermometer to do that. You're not going to do it with a standard K-type bead probe thermocouple. That might be plus or minus 4 degrees, right? So that's a very inexpensive solution, but it gives you a very inaccurate measurement when you look at a measurement uncertainty of 1 degree. Now, if we're, and that's why sometimes you got to spend a little bit more money on instrumentation when you're looking at, what's the degree of uncertainty we're allowed to have. But here's where we get into a problem. A lot of technicians, when they talk about hitting the target, that means charging the target to the edge. In other words, if we're required, 15 degrees of superheat, and a technician gets to within 20 degrees of superheat, he goes, okay, well, perfect, right? I'm right at the edge. I have plus or minus 5, and I'm at 20, and okay, so I'm good. I'm within 5 degrees. Well, what he didn't consider is what's outside of this blue circle, which is the measurement uncertainty. There's still a 50% uncertainty that the technician didn't get the measurement right because he hasn't taken into account the measurement uncertainty. Yeah, he's within 5 degrees of the target, but how close is his measurement? And this is where, when we look at overall how accurate we got to be, if you don't take into the uncertainty into account, you're going to get yourself in trouble. Analog technology and a related inherent error make the uncertainty overshadow the target. In other words, you say plus or minus 5 degrees, and if you were exactly, if it called for 15 degrees and you were exactly at 15 degrees, there's still so much uncertainty in your measurement, so much uncertainty in your measurement that you really probably aren't where you think you are. And a lot of technicians, including myself, I didn't realize this for years as I was doing this type of work. It causes our substandard instrumentation. You're trying to do a job with the wrong tools. A lot of us buy tools simply because they're cheap, they're inexpensive. We want to find a low-cost solution, and so we use the wrong tool for the job. Out of calibration. When you buy certain types of measurement tools like K-type thermocouples, they're not accurate out of the box. When you take one of those and you plug it into your meter, you have to go through a calibration procedure, and if you're not doing that, you don't know how accurate that K-type thermocouple really is. Could be a lack of training. Simply, how do you attach that thermocouple to the pipe or the clamp to the pipe? Where do you attach that? Pipe diameter plays some things in with that. If we have a larger pipe diameter, we might want to be at the 4 o'clock position on the pipe. So we got to make sure that we understand where to make the measurement at, and simply incorrect measuring techniques. If you were to look at measurement uncertainty, and we just took a type K standard bead probe that somebody would use and a gauge, low side, plus or minus 2.4 to 3.5. So I'm looking at the 1% and the 323, and plus or minus 8 to 10 on the high side. Here's what you got to realize. First of all, both the gauge and the thermocouple very easily lose their calibration. Now, if first we're talking about a gauge that's perfect, right? A perfect gauge is, you look at the 323 gauge, it's 3.5 pounds plus or minus 3.5 pounds, so we're talking 7 pounds of span here. If it falls anywhere than that 7 pounds, it's considered accurate. And a high side, plus or minus 10, so anywhere than a 20-pound span is considered accurate, right? And then we got a K-type thermocouple, plus or minus 4, right? So you start adding up, because you got to remember now, to calculate superheat and subcooling, we've got to make a pressure measurement and a temperature measurement, right? So we've got to look at both halves of the equation here. And you also got to remember that board-on-tube gauge has been bounced around the back of your truck. You tossed it in your 5-gallon bucket at the end of the day. Your K-type thermocouple could be affected by voltage, stray voltages. It could be you pulled a meter out of your truck that's hot, that's maybe 110 degrees, and you're putting it on top of the roof or setting it, out in the ambient, and the cold junction and hot junction aren't the same temperature anymore. There's issues there that you have to make sure that you address with your measurement solution. Now, if you contrast that with a digital gauge set that uses thermistors, and Testo's not the only one. digi-kool does also, and I'm sure there's some other ones out there. But looking at it now, instead of plus or minus 4 psi or 4 degrees Fahrenheit, a thermistor is typically plus or minus 1.8. In transducers, because we're using a transducer to measure pressure, which they're typically made of ceramic, and they're typically 0.5%, they're much more accurate. And the other thing we can do with a pressure transducer is we can select a lower range pressure transducer. In other words, if our working range is, let's say, 0 to 200, right? We could actually use a pressure transducer that has that lower working range, and we could expose it to maybe 500 psi and not damage it, because the transducers are a lot less susceptible to damage than a board-on-tube gauge is. So there's some advantages to that. We can select transducers that are closer to our span, our desired measurement span, without the fear of damaging. And we can't really do that with a board-on-tube gauge. If we were, we have to make sure that the gauge, if we're going to use like that R22 410A gauge, we got to make sure that that the pressure range is high enough to handle the 410A without damaging the mechanics of the gauge. Now, I always, I don't like just pulling statistics out of the air and having you believe me. And I just wanted to show you here, and this is from the International Journal of Sensing for Industry, Volume 21, 2001. Thermocouples have low accuracy. 1 degree C is common. They have noise problems, high noise problems, and they have low long-term stability. All right? When you get into a thermocouple also, you have to consider the enclosure that it's in. You know, everybody goes, oh, K-type thermocouples are so fast. Well, yeah, they are. They really are to get a bead-type thermocouple probe. But you also have to remember if we incorporate that bead clamp into a clamp probe, it's going to slow that thing down. It's going to make it more comparable to a thermistor. So, well, the beads are very quick. They're really only suitable for measuring airflow, not for really measuring pipe temperatures. Just to give you an idea here of the typical analog gauge, what this means to us, if we were to take R22 at 220 psi, right? So right at the top there, 220 psi, at plus or minus 10 psi, okay? So plus or minus 10. So we're at 220 there. The low here would be 220 down to 210, right? And then 220 up to 230, okay? So these are the two we're going to look at right here. Well, again, what did I tell you that we had to be on Energy Star determined we need to be within what? Plus or minus 3 degrees. Well, just look right here from 108 down 10, that drops 5 psi. Right there's 3 degrees that way, and right here's another 3 degrees this way, right? So we're already talking plus or minus 3 degrees of saturation. We have a temperature uncertainty of plus or minus 4 degrees. That makes a total uncertainty of 10 degrees of uncertainty. There's no way with an analog gauge set that we could even be close. If we look at 410A, right, and at 359 on there, now we're looking at a low of 107. Okay, so we're here, and we're looking at a high of 111, so we're right here. Again, right, we have a 2 degree swing, plus our uncertainty, so we're at 8 degrees total uncertainty for 410A. And again, we have all the same inherent problems. We simply cannot meet the targets the manufacturers want with this technology. Now, if we shift and we go to look at the same condensing temps now with a digital, with a 0.5% accuracy. Now we're looking at plus or minus 2.5 psi. So again, we're going to start here with 220, right? At 220, plus or minus 2, well, the low goes to 107.5 and the high goes to 109. You can see we don't even change 1 degree in saturation temperature, right? Because this is 216. So we don't even change by a degree in saturation temperature. And we've got a temperature uncertainty of plus or minus 1.8. So that takes our total uncertainty between 2.3 and 2.8 for R22 or 410A, right? So we're talking about now much, much higher accuracy. But this doesn't get us off the hook altogether, and I need to cover some things in the next slide or so here to explain that. But you can see when we go to a digital gauge, because we have the higher accuracy transducer and the higher accuracy thermistor, we're going to be able to hit these targets now. So with digital gauges, what we've essentially done is we've got a smaller uncertainty and a higher accuracy. And you got to remember too, we've eliminated some human factor because we're not interpolating anymore off a temperature pressure chart, and we're not trying to split hairs on a needle with a gauge. The gauge calculates right down to a tenth of a degree Fahrenheit and down to a tenth of a degree of superheater subcooling and a tenth of a psi. So the probability of correct charge is significantly increased. Now, I told you we weren't off the hook yet, and let's just talk about what's the allowable range as a function of superheat and subcooling. Because, again, if we talked about a gauge that had no uncertainty, in other words, we had no uncertainty in our subcooling measurement. In other words, it is exactly what we say it is. If the gauge said it was 10 degrees of subcooling, it was exactly 10 degrees of subcooling. Now, even with a high-end digital gauge, 0.5% accuracy, we said we're plus or minus 2.8, right? Well, we have to be, if you're talking 2.8, you're talking this right here between 2 and 3, right? We're talking right in this area here. We have to be within 1.2 to 1/10 of a degree of our subcooling. Basically, when we look at it this way, we have to be within 1 degree. So if it calls for 10 degrees of subcooling, we need to charge the system to exactly 10 degrees of subcooling to be within plus or minus 3 degrees, right? We've got to be within that 1 degree. So you have to take the time to actually set the equipment up properly to nail that target as close as possible. Otherwise, you're not going to be within the manufacturer specified subcooling. And this becomes very, very important to do correctly because it directly impacts the performance of the equipment. When we look at an analog gauge, it's absolutely impossible. So if you're installing these high efficiency systems with analog gauges, you're probably not getting your charge correct. Okay. Now, if we're talking a fixed orifice system, and you can be, and our total uncertainty is plus or minus 5 degrees, well, you have to be within half a degree of the target superheat. You may be able to do it, but I doubt it. Okay. So this is where it's become critically important. And we talked a little earlier in one of the earlier classes, high efficiency systems are sort of like race cars, if anybody's into racing at all. The difference between a 13-second car and a 10-second car is a lot of money and a lot of tuning and a lot of work. You just can't make a production 10-second car and have it be reliable. I mean, these are race cars. And we've done the same thing with high efficiency equipment. We're selling somebody an 18-SEER piece of equipment today. And that 18-SEER piece of equipment has to be set up exactly right to get 18 SEER out of it. If your airflow is off or your charge is off, you're going to just start dropping off in performance. And that's not what you're selling your consumer, and that's obviously not what we want to do when we're putting in the new equipment. Simply, if you haven't just considered digital, you need to look at it because it allows, it's going to reduce your callbacks, calculate without human error. We're going to stay in calibration, and really we're going to increase our repeatability and reliability substantially. Measurement technology-wise, we talked about this. This is a little picture of a transducer and what they look like. But unlike the mechanics of a gauge where we actually got a board-on tube, which is a curved piece of copper and gearing and all that kind of stuff, we've gone to a solid-state pressure transducer, which is ceramic, which is highly resistant to corrosion, has very good linearity and low hysteresis, which a very wide temperature range and good long-term stability. So let's get into charging now, because we hit, we got to have the correct charge and some of the things that are going wrong with charge. So let's talk about that. When talking about charge, we're talking about the proper mass of refrigerant that allows the system to operate at its optimal state for reliability, capacity, and efficiency. That means there's pretty much only one correct charge. You've got to nail the numbers. We verify it's correct by superheat and subcooling. And weighing in the charge does not guarantee proper operation, right? I don't care what manufacturer you deal with, all right, because I talk to people that put in mini splits and put in large commercial systems and all kinds of stuff. Somewhere down the line, the manufacturer has charged that system up by superheat and subcooling. So if you're putting in a packaged rooftop and it tells you that it requires 10.2 pounds of refrigerant, somebody has charged that system up using a subcooling or superheat method to get that charge exactly what it should be, and then they weighed that refrigerant into the system and know how much exactly has to go back into that package unit, right? But all systems are charged by superheat and subcooling. And if you really want to think about it this way, what they continue to do, you start with an empty system, and the manufacturer will add charge to the system, and as they add charge to the system, the capacity increases, the amount of cooling increases, it goes up and up and up, till eventually it reaches the maximum amount of cooling that system is capable of doing. If we add any more charge to the system, then we're going to start to get a decrease in capacity because we're going to back refrigerant up in the condenser, or we're going to raise the evaporator pressure up if it's a fixed orifice device, but we're going to start to drop capacity off. So it's this balance, this perfect balance between the exact amount of refrigerant and the optimal cooling capacity. And once they figure that out, then they have a variety of methods that they charge the system. We're going to go over some of those now. You've got to remember when we're charging up a system, okay, putting on your gauges is typically the last thing that we want to do. We don't want to just throw gauges on a system because that doesn't tell us anything about the system performance if we have things like this, a completely plugged evaporator coil, right? The plugged evaporator coil is going to indicate low suction pressure, and that low suction pressure is going to throw us off. You know, when I was younger and I first got in this industry, when I saw low suction pressure, the first thing I did was add gas because I wanted to get the suction pressure up. I didn't realize the impact airflow had on refrigerant pressures, and I didn't realize that a block evaporator coil would cause problems. So before we do anything, we have to evaluate the system. You know, things like this. This is an evaporator coil that was put up on slips and drives over an oil furnace. Air is bypassing the evaporator coil, and that air bypassing the evaporator coil means the air is not going through the coil. So even though if you were to measure the airflow in the return, it might look exactly correct, because the air is going around the coil and not through it, we're going to have a compromise in performance. These are things we got to look for when we're doing inspections. Dirty blower motors, dirty wheels, dirty filters. If the system is filthy dirty, it's not going to move the correct amount of airflow. Right? Here's another picture. This was actually our sales guy's house, Eric. Some of you guys dealt with Eric before. We stopped over and we did an inspection of his system at his house, and I wanted him to walk him through step by step what a technician has to do. And when we got a scope up inside there, you can see that there's about a 3/4 of an inch bypass around his evaporator coil, and that bypass was causing his coil to get plugged with dirt because the coil, that half the coil didn't have the correct amount of airflow through it. It was getting excessively wet, and it was just a giant dirt magnet. And so we had to clean this evaporator coil off, chemically clean it, washed it off, fixed the bypass in the coil, and then obviously also we had to go outside and clean the condenser because his system, it's an older rude system there, and it's got a fixed orifice in it. And with a dirty condenser, you're going to drive up the head pressure. When we drive up the head pressure, we're going to force more refrigerant into the evaporator coil. So everything, when you go to hook up gauges to a system, the very first things you got to make sure of before you try and evaluate anything with charge at all are, is the condenser clean? Is the evaporator clean? Is the airflow correct? Because if those things aren't done first, you're wasting your time. You cannot get the charge correct on any system without cleanliness and correct airflow. It's absolutely impossible. And there's no use connecting gauges to a system before we do that. You think about your refrigerator at home. You know, if your refrigerator wasn't cooling well at home, the first thing, you know, I hope nobody would go and grab a piercing valve and check the charge in the refrigerator, see if it's out of refrigerant, right? Everybody knows, get the vacuum out, vacuum underneath it or vacuum behind it, clean it out, make sure that, you know, if we got filters, the filters are clean also, right? But we're going to make sure that all those things are done first so that the system can operate at its optimal performance. When we talk about charge, systems come with enough refrigerant for a matched coil and typically 15-foot of line set. This is one of the big reasons that systems are not charged properly. You know, we got all these guys out doing new construction work, and a lot of times, you know, new construction is done off-season, and nobody ever comes back to check the charge on a system unless somebody calls and complains, right? So the system gets put in. It may have 30-foot of line set, 50-foot of line set, may have 10-foot of line set, could be overcharged, could be undercharged, but unless somebody calls and complains, sometimes the homeowner just figures that's the way it's supposed to operate. You know, it's supposed to cost them this much money. They just moved into a bigger house. They have no track record with it, so they don't call, and it just runs that way until somebody comes out and actually properly commissions the system. Things like length and lift will impact the charge requirements, so you got to make sure that, you know, those are taken into consideration. And if we're talking excessively long line sets over 50 feet, you got to make sure that you consult the manufacturer's requirements, because it may even require you to change line sizes to accommodate the pressure drop in that liquid line. You may have to go up a line size when you get into longer line sets. If you can, weigh-in is usually the best way. If we're talking like a package rooftop unit, and I deal with guys that do refrigeration all the time, and they go, man, I never check superheat or subcooling. You know, I may verify it, but I don't charge that way because everything we work on is packaged, so I just weigh in the charge. Well, that's great if you know what the correct charge is. Most of the time we're talking about a system that is installed in the field, and we have an unknown, which is the line set length, and maybe the evaporator coil, maybe there's like 2 or 3 different evaporators you could match up with it, but we don't know what size evaporator we got, so we have a bunch of unknowns. The great thing with the weigh-in is if we know how much charge is supposed to be in the system, It can be done all year. And the airflow, though, before we can evaluate it, we got to get the airflow set, and it's got to be evaluated under proper conditions, because weighing in the charge doesn't guarantee proper operation. The TXV could not be installed correctly, or you may have a restriction in a line set, or it may be a kinked line or another issue in there. You've got to still go back and commission the system. We can't just go, well, it's winter time, and I'm going to go ahead and install a system out there, and I'm going to weigh in the gas and how much it takes, and I'll be fine. You got to make sure that you actually go back and properly commission that system and check both the superheat and subcooling. So let's go over the fixed orifice system, and this is the one that's probably more common than anything, and a lot of guys out there still don't know how to properly charge this. So I want to go over some things with this that will help you guys understand how they work. When we look at ARI design conditions, okay, a fixed orifice system is engineered to operate under one set of conditions, just one set, that's it. 80 degrees indoor dry bulb, 50% relative humidity with 95-degree outdoor air entering a condenser. And that's the only target that the manufacturer has to engineer that system to operate under. So typically, those systems will operate a little over capacity or a little under capacity depending on the load conditions. The only time they'll operate at their optimal capacity is when they're running about 10 to 12 degrees of superheat at the evaporator coil. If they're not running near that 10 to 12 degrees of superheat, it's operating at a different capacity than it was engineered for. Now, that doesn't mean that it's supposed to operate at 10 to 12 degrees, because the superheat varies with load conditions. Now, let me show you some interesting stuff here to start with. So if we're going to take, this is a psychrometric chart, and a psychrometric chart is simply relationships of air. Psychro is the study of air. So what we're looking at here with the center circle is we're at a 50% relative humidity line, and these curved lines going up here, these are relative humidity. So that curved line, if we follow that up, crosses this point here, and it goes right through that red dot on my screen. And then if we plot the corresponding wet bulb temperature, which is right here, this is 65, 66, 67, and here's what I want to show you is that 50% relative humidity at 80 degrees dry bulb, which is down here at the bottom, that corresponds to a 67-degree wet bulb temperature. All right? So the ARI design, when we talk about, because when we look at a charging chart here in a minute, it's not going to give us relative humidity, it's going to give us wet bulb. Wet bulb is simply takes into account heat and humidity, because an air conditioner removes two types of load. It removes sensible load, which is heat, and it removes latent load, which is humidity, right? So the humidity plays a big impact on how the system performs. The higher the humidity is, the more work goes into converting water vapor in the air into water. So when the humidity is very, very high in a home, most of the work the air conditioner is removing is dehumidification. As the humidity drops in a home, more of the work goes to cooling it or dropping the temperature. And we'll go over some of those relationships in the next couple slides here. So here's, if we consolidated the ARI conditions, and it's actually AHRI now, they merged with ARI merged. We're looking at a 67-degree wet bulb with a 95-degree outdoor air temp. When it's close to design, when it's operating close to that design, we'll have 12 degrees of superheat and 10 degrees of subcooling. Now, I pulled up a chart here just to show you this, and I always thought this was pretty cool. This is a target superheat chart, and I'll show you where you can download this for free off of our site when you're done. This is a simple target superheat chart, but you can see here, this is a condenser dry air entering temp on the left, right? This little line right here is condenser dry bulb entering temp. So I have it highlighted here at 95 degrees outdoor air temperature. And if I take that across till I correspond to a 67-degree wet bulb, you can see right here in the middle, it corresponds to 12 degrees of target superheat. So under the ARI design conditions, 95 and 67, that system would be exactly 12 degrees of superheat. That's the typical target superheat. And that whole chart is sort of derived from this, okay? So, and I'll show you a little bit how this works in just a second, but I just wanted to show you, when we talk about 12 degrees being target superheat or typical superheat, that's where it came from. But you can see as those load conditions change, right, as the wet bulb temperature goes up from 68, 69, 70, well, that target superheat goes to 13.9, 15.8, 17.8, 19.78. It increases also. And you can see as the outdoor air temperature goes up, the target superheat goes down. And we'll look at these relationships in more detail here in a second. we're talking a fixed orifice system. This is, again, cap tube, piston, right? Here's the metering device. All the refrigerant goes right through the center hole. It actually goes all the way through that hole and out the other side. And these are to bypass, if it's in a heat pump, the refrigerant will go through the center and around the outside in a bypass position. But in normal way it works is this gets front seated and against this gasket, and all the refrigerant is forced to go through this little metering device. These are critically charged systems under all load conditions. Okay, when we were looking at that superheat chart and it said, 15.8 degrees, it means 15.8 because it's 15.8. That's what it needs to be charged to. So you need to be within a degree or two of the target superheat. Otherwise, you're going to be undercharged or overcharged. It's charged by the total superheat method, which I'm going to review here in the next couple slides. It has a target superheat which must be calculated or derived. Now, again, we usually use that charging chart, but there is a formula to calculate target superheat if you want to do that, and I'd have to dig it out real quick. I always use a chart just because it's more convenient. And it varies with capacity and load conditions. It's simple, but not as effective at removing heat and humidity. The metering device itself is. It's a very simple metering device, and it's inexpensive, and that's why manufacturers use it, but it's not as efficient as removing the heat and humidity under the varying load conditions. So, why do we use a fixed orifice? Cost, inexpensive. Why do we use a TXV? Efficiency and better load control. When you look at a fixed orifice system, okay, I always call these seesaw systems, because what happens here, let's just think about what happens on our condenser side. A fixed orifice system is simply a hole. It has no way of opening or closing or changing the size of that hole. So simply if we drive the pressure up on the condenser, and that's what we're doing on this side of the system on the right-hand side here, you can see where my arrow's at. If I, oops, well that's an ugly arrow. Let me see if I can undo that. Nope, never learned how to do that one. Let's see here, pointer options. Erase all ink on slide. There we go. All right. My mouse is getting a little squirrely here. All right. If we raise the pressure on that condenser, right, push down, think of it as a seesaw. It's going to lift up on the evaporator side. So as we push down here, that's going to mean a decrease in superheat. Okay? So as we increase the pressure, we're forcing more refrigerant into the evaporator, and the superheat's going to go down. Okay? So that means, and if we go the other way, if we increase the pressure on the evaporator, it's going to drive the superheat up. And I'll show you this on the chart on the next page here. Oops, let me see if I got it here. Okay. So if we're looking at a constant indoor wet bulb temperature, as the air temperature increases, this would be the evaporator side, right? Sorry, at a constant wet bulb, 67-degree wet bulb. As we increase our pressure on our condenser air entering dry bulb temperatures, that goes up. So you start here at 55, our target superheat's 33.8, right here, 33.8. So it's 67-degree wet bulb, 55 degrees outside, target superheat's 33.8. If we increase that to 65 degrees, right, well now we're at 28 degrees. When we increase the pressure on the condenser, we're driving more refrigerant into the evaporator, and the target superheat's going to go down, right? Pretty simple. Outdoor air is a driving force. So as the outdoor air temperature changes, the target superheat changes, right? And basically at a constant indoor wet bulb, as the outdoor air temperature increases, superheat decreases. That's a relationship you have to know. You don't have to remember it. You can look at your chart and you can see it right off your chart. If we take a look at a constant outdoor air temperature, right? So now we say, okay, well, what happens if it's just 75 degrees outside? Well, you can see as the return air wet bulb temperature increases, as it goes up, as return air wet bulb goes up, our target superheat also goes up, right? So the load, the heat and humidity, also has an impact on the performance of a fixed orifice system, right? So these are things relationships we got to make sure we understand, because on a fixed orifice system, we got to measure outdoor air temperature and return air wet bulb accurately to determine the target superheat. If any of those load conditions change, our target's going to change. So as you're charging a fixed orifice system, one of the things you have to make sure you do is you have to go in and periodically check your return air wet bulb temperature and make sure the wet bulb hasn't changed, because if your wet bulb drops by a degree or two, your target superheat is going to drop also, and we'd have to readjust our target. If we go back a couple slides here, you can see here if we're charging by total superheat, we've got to measure the outdoor dry bulb, measure the indoor wet bulb, and charge by the total superheat method. Now this is a wet bulb thermometer. It's an older Tesla 605H2, but this is the type of a tool we're going to use to measure return air wet bulb temperature. All right, so when is the charge correct? Well, when the actual superheat and the target superheat agree, the charge is correct. Now, we always have to evaluate both sides of the system, because, you know, everyone say, well, how much subcooling going to have? Well, I have no idea, right? How much is a question. It could be as little as 3 and as much as 30. Because, you know, we said before, if we had 12 degrees of superheat, we probably have around 10 degrees of subcooling. That's pretty much the way that system's going to be designed to operate. It's operated to operate at a single set of conditions. So it's going to operate pretty much like a standard TXV system would under those design conditions. But when we change from design conditions, because its target superheat goes up and down, the subcooling changes also. Remember, this is a sealed system. So the refrigerant's either in the evaporator or it's in the condenser, right? If we have low superheat, well, we're going to have low subcooling because we've flooded the condenser. If we have high superheat, we're going to have a lot of subcooling because now we've starved the evaporator and we've flooded the condenser. So these things change. In a fixed orifice system, we only evaluate charge by the total superheat of the system, but we check subcooling to make sure it falls within line. Okay? So that's just something to remember. All right, let's talk a little bit about TXV systems. Let me see, I'm going to peek at some questions here, see if I have any over here that I need to answer real quick. Let me see if I can drag this thing down. This WebEx thing, I've never quite figured out how to grab those questions and make that box bigger. There we go. All right. Had a couple questions here is with weighing in, what is the amount of freon to be considered for a filter dryer? That's a good question. And I couldn't tell you right offhand. And if you're going to weigh it in, you're going to be exactly accurate. You would definitely have to know that. And I think it would vary from manufacturer to manufacturer filter dryer because the type of medium that they use as a desiccant to absorb the moisture. Sporlan uses a solid core filter dryer, which probably would take a lot less liquid capacity than a dryer that uses fiberglass, filters and some kind of a bead type desiccant. That's a good question, one I'd have to research to give you a better answer on. I couldn't tell you right offhand. I would end up charging, again, probably having to check that charge, weigh it in to get it close, and then check by superheat or subcooling. It's somebody stuck on the ARI slide. Todd, if that's still a question, problem, shoot a PM over to Bill. We'll see. I'm not sure what would be causing that unless your side froze up. Is there a target? Okay, good. Is there a target subcooling chart? We're going to go over that in just a second when we get into the TXV system. So let me keep moving on here. All right. So TXV systems, they're critically charged at full load, and the charge is verified by condenser subcooling, and it maintains a constant superheat. Well, if we get this thing set up right, it maintains the constant, and I should actually add in the word in there, evaporator superheat of 8 to 12 degrees. There's two types of superheat in the system. There's evaporator superheat and there's total superheat. Evaporator superheat is the superheat that would be measured right at the evaporator outlet that the TXV is controlling. You got to remember the bulb, the TXV sensing bulb is mounted at the outlet of the evaporator. It really can't control superheat after that bulb. It has no idea, if you ran that suction line across the 100-degree roof for 300 feet. All it knows is it's maintaining 8 to 12 degrees of superheat at the evaporator coil. It can't tell after the evaporator coil what's going on. So your total superheat, and would be the total superheat is the superheat measured at the condenser inlet, right? And that's typically where we measure superheat when we're charging a fixed orifice system. That, again, even though we're maintaining a constant evaporator superheat at 8 to 12, that could be anywhere from 12 to 20, 25 degrees of total superheat by the time it gets to the compressor. If the total superheat is too high on a TXV system, the solution is not to adjust the TXV to get the evaporator superheat lower and the total superheat lower. What you really have to do is insulate that suction line better so that it doesn't pick up as much heat between the time it leaves the evaporator and the time it enters the condenser, right? That's really, it's an insulation problem. You got to have that line better insulated. The beauty of a TXV is it maintains capacity under a wide range of load conditions. So it's always going to try and maintain the exact same level of refrigerant in the evaporator all the time. And what's interesting is that if the refrigerant evaporator level never changes, neither does the condenser. So when you think about how a TXV system is charged, when the manufacturer calls for 10 degrees of subcooling, it's not 10 degrees of subcooling on a mild day and less on a hot day. It's 10 degrees all the time because the TXV's job is to maintain superheat. Now, it doesn't operate, a TXV won't operate under a range of superheats. When I say 8 to 12, typically it'll maintain within 1 degree. So the valve could be set at 8, 10, 12, 11, who knows what it's set at. We have to measure that to see what it's set at. But the manufacturer static sets the valve. In other words, they set it by spring pressure at the factory, and it's set at what it's set at. So when we check superheat on a TXV, it should fall within 8 to 12 degrees, but it's going to try and maintain what its setting is. So if it's set at 12, it's going to always try and maintain exactly 12 degrees, plus or minus typically 1 degree of superheat. As soon as it sees it's dropping down to 11, the valve's going to start to shut. If it's going to go up to 13, the valve's going to start to open again to try and maintain exactly 12 degrees. The difference between the opening point and the closing point of the valve is the hysteresis of the valve. That's how much does it change before the valve responds. And that can be as tight as half a degree. And when we get into electronic expansion valves, it could be as tight as 1/10 of a degree. So it's the valve is trying to maintain the level of refrigerant in the evaporator constant all the time. And so, again, the condenser side doesn't change. So the condenser, if it calls for 10 degrees of subcooling, it'll always operate at 10 degrees of subcooling, provided the coils are clean and the airflow doesn't change and things are operating under a normal condition. Doesn't matter whether it's 65 degrees outside or 105 degrees outside, you should still have that 10 degrees of required subcooling. Now, subcooling will vary with design. So sometimes if we have a lot of length and lift, we may be required to have a little bit more subcooling. And if the manufacturer doesn't give you the required subcooling, typically 10 to 12 degrees of subcooling is adequate. You've got to remember, we're measuring subcooling at the outlet of the condenser coil. By the time it gets to the inlet of the evaporator, which is the inlet of the metering device, it's gone anywhere from maybe 10 feet to 50 feet. There could be a substantial pressure drop in that liquid line, and with that pressure drop comes a temperature drop. And basically what will happen is, if we have a very long line set, is the pressure drop will cause a refrigerant to flash into a gas, and we'll lose our subcooling. So we may have 10 degrees at the condenser outlet, but because of a huge long line set and maybe a lot of lift, there's so much pressure drop that we have maybe 0 degrees of subcooling by the time we hit the expansion valve. Right, so sometimes you're talking about excessive length, line, and lift. You may have to increase your subcooling from maybe 10 degrees to 12 degrees or 13 degrees of subcooling to compensate for that drop in pressure. And really the correct way of doing it is to increase the liquid line size so that we decrease that pressure drop. And that's where it's said, if you're going to a longer line set, consult the manufacturer to see how they want you to correct that problem. Maybe a slight increase in subcooling. Maybe you have to change the liquid line to make it operate correctly. The beauty of it also is it's going to give you better relative humidity removal under a wide range of loads because it's always maintaining a constant level of refrigerant in the evaporator. The coil is not going to be ever starved, and it's not going to ever be dry at the top of the evaporator coil because it's not completely full of refrigerant. It's capable of maintaining a constant suction pressure independent of the outdoor air temperature. And what this means is a TXV, as it gets hotter and hotter outside, right, the condenser pressure goes up, the TXV simply closes down, right? It's the suction pressure is not going to get driven up with an increase in outdoor air temperature because the TXV has the capability of actually closing down. And now it doesn't maintain suction pressure. The suction pressure a TXV sees is simply a function of the load. It's a function of the temperature of the air going across the evaporator coil, but it does respond to changes in superheat. So if we were to drive up our outdoor air temperature, we'd also drive up our pressure. Well, that pressure is going to force more refrigerant in the evaporator. When we force more refrigerant in the evaporator, the superheat is going to drop, and as the superheat drops, the TXV closes to control the amount of superheat in the evaporator coil. If it's installed properly, if the TXV is installed properly, it's as reliable as a fixed orifice. I hear time and time again, oh, I hate TXVs, they're horrible, I have a lot of failures. Well, TXVs are a precisely manufactured piece of equipment. If you're going to install high efficiency equipment, you got to use correct practices. That means you do a proper evacuation and a proper installation. Tubing has to be deburred, and those burrs can't end up in the tubing. The system should have nitrogen purged through it when you're brazing it, because copper oxides can plug up the inlet filter to a TXV. That filter dryer needs to be installed at the time of installation. If you do the steps properly as you install the system, the TXVs almost never fail. In fact, in 20 years, I can say I've probably changed 2 or 3 TXVs, and they're typically due to vibration failure of the bulb capillary tube breaking. Somebody didn't clamp it down. It was an installation error. I don't think I've ever had to replace a TXV. Sorry, sneezed because the TXV failed itself. When we talk about where do we position our probes, the probe positioning is critical to proper operation. You got to remember, we're always limited, where we put the probes by simply where we have points to measure pressure. There's pressure drops in the line, and it's real important if you're going to try and quantify superheat and subcooling at a point that you measure pressure and temperature at the same location. So if we're talking a TXV system, we're going to measure subcooling. We have to measure the subcooling at the condenser outlet. That's typically the only place we have a port to measure pressure, right? Unless you install another port at the evaporator, or the manufacturer installs a port, and Trane does that on some of their units, where they'll have a port inside. Unless they install that port there, you're limited to 2 points. We can measure subcooling at the condenser outlet and superheat at the condenser inlet, right? And so if we're talking about superheat at the condenser inlet, we can only measure total superheat, right? And that's why we charge a fixed orifice system. If we're charging a TXV system, we're going to measure subcooling at the condenser outlet. And again, that's subcooling 10 to 12 degrees if the manufacturer doesn't tell you otherwise. If it tells you on the label, then you charge it to exactly what the manufacturer requires. If it says 11 degrees, take it to 11 degrees. That's where the optimal performance is going to be. TXV systems find the required subcooling from the equipment tag, charge directly to the subcooling requirement level. So in this case, this unit I was working on a couple years ago, this is an older Testo 523, required 8 degrees of subcooling, and we're right at 7.5 degrees, right? Now after we're done, we need to always verify both sides of the system to make sure that if we have the correct amount of subcooling, we also don't have excessive amounts of total superheat. In other words, we said 8 to 12 degrees of evaporator superheat, and if we have a port at the evaporator outlet where we can measure, that's where we're going to measure it. But if we don't have that point, what we're going to have to do is we're going to have to look at total superheat, and typically that total superheat should be between 12 and 20 degrees. If we get over 20 degrees of total superheat, you better add insulation to that line set, because you may not provide adequate cooling for the compressor, and you may have a failure there. There's 2 things we don't want to do. We don't want to flood a compressor with liquid, so we always want to make sure that our superheat's not too low, right? If we're getting 3 to 4, 6 degrees of superheat at the condenser inlet, well, that's pretty low superheat. And that doesn't mean you're over-insulated your suction line. That means for some reason your TXV is overfeeding. Maybe you have a loose bulb. Maybe you don't have a good connection of the valve. You got to look at things and see, okay, loose connection of the bulb. Maybe the bulb's not properly insulated, it being influenced by temperature. you got to start looking at the TXV installation to see what the problem is. Why is the TXV overfeeding, right? So we always evaluate both sides of the system. Don't just assume because you have a that you have correct subcooling that your superheat's fine. You got to look at both sides. For the TXV to operate properly, the metering device needs at least 4 to 6 degrees of subcooling immediately before its inlet. Now, as practice, I typically install a port on the liquid line right before it enters the TXV. That's just me. And what I can do there is I can go across, I can go in the house, connect my pressure port there, connect my temperature port there, and I make sure that I still have subcooling before I enter the thermostatic expansion valve. Most of the time, you don't have to do that unless you suspect a problem. It's a very easy way by adding that port in there. It's a very easy way to just make sure your liquid line's not undersized or kinked or there's a problem with it. If we don't have that subcooling, we're going to get flash gas. And flash gas simply means that the refrigerant has dropped down to a saturation temperature, and now it's no longer subcooled. It's not 100% liquid. It's actually a mixture of liquid and vapor. And that flash gas lowers the system efficiency. If you've ever had air in a spigot when you've gone to draw some water out of a sink, and you know how that air splashes and spitters and sputters out of the faucet, it's exactly what happens inside the TXV. You don't get that nice smooth laminar flow, and it's very, very hard on that metering device. It causes liquid hammer, and it can actually ruin the metering device over time. And temperature drop in that liquid line can indicate problems. So typically, what's a really easy thing to do is to measure the temperature of the liquid leaving the condenser, and then measure the temperature again where it enters the metering device. If you have a liquid line drop, typically much over 3 to 4 degrees, well, it could indicate that you have an undersized liquid line and you're actually having some problems there. Now, obviously, you could be running across a hot roof, or you could be running through a cold area and also cause changes in liquid temperature. Barring those things, and obviously you'd have to take those into consideration. That's why it can indicate a problem. That's a thing you want to check. You can also install a sight glass right before the metering device if desired. Now, there's 2 reasons that you would do that, and you got to watch. Sometimes when we have blends of refrigerant, some blends will have some small bubbles in the sight glass, and that's completely normal. But the reason that I like to install a sight glass before the TXV is simply to make sure that the refrigerant's dry, right? Because usually it has a moisture indicator that turns green when you have dry refrigerant in there. Not so much to see if there's 100% liquid in there, although you can do that, but to indicate the refrigerant's dry before it enters the metering device. There's a couple of relationships you got to make sure you understand, and you'll hear some different terms out there, and one is approach and subcooling, and then condensing temperature, CTOA. You hear these things. I want to make sure we cover what they are. The coldest, if you think about ambient temperature, if the ambient temperature was 93 degrees, right, the coldest the liquid line temperature could ever get is 93 degrees, right? The liquid line temperature cannot get any cooler than the ambient air temperature. It's impossible unless there's a problem, like a pressure drop in the condenser. Like you may have an issue where the condenser's got a restriction in it. Sometimes they put liquid line filter dryers in the condenser, and you'll be going out there and you'll be measuring the outdoor air temperature goes 93, and all of a sudden your liquid line temperature is 90. Well, how's that possible, right? Because the condenser is rejecting the heat, and the air is what's cooling the condenser. So the coldest the liquid could get is down to the same as the ambient air temperature. Well, if you drop below that, you got a restriction in there, and that's covered in our guide there. We have to troubleshooting refrigeration systems. There's a guide online. I'll show you when we're done. But typically what we'll see is that the liquid line is always warmer than the outdoor air temperature, and the condenser saturation temperature is above your liquid line temperature. Okay? So when we talk about approach, you hear the term approach. Approach equals the liquid line temperature minus the ambient temperature. So in this case, if our liquid line temperature is 101 and our ambient temperature is 93, right? 101 minus 93, you have 8 degrees of approach. Subcooling is a condenser saturation temperature minus the liquid line temperature. Here, our condenser saturation is 110, our liquid line temperature is 101. 110 minus 101 is 9 degrees of subcooling. And we talk about condensing temperature over ambient. It means how much higher is our condenser temp than our ambient temp. Well, here our condensing temp is 110 and our ambient temp is 93, so there's 17 degrees difference. The saturation temperature of the refrigerant is 17 degrees above the ambient temperature. That's considered split. On old systems, the old low efficiency, we used to say the condensing temp over ambient was 30. Everybody used to say, oh, yeah, it's got to condense 30 degrees hotter. Well, as these systems have gotten higher and higher efficiency, right, you get up to 18 SEER condenser, that's no longer plus 30, that might be plus 15, because that higher efficiency condenser is larger, so to reject the same quantity of heat, it needs to be at a lower temperature than that older, smaller condenser that was 30 degrees hotter. And those are just some relationships you need to have in the back of your mind. Now, one of the things, too, I wanted to make sure that everybody understands, and this is a graph I did on a Testo 570, well, probably one of my favorite instruments we have because I'm a big data logging buff. And this was actually on my unit at home, and I just want to show you some relationships here to make sure you guys understand some stuff. You cannot go outdoors and block the condenser on a high efficiency unit to try and increase the head pressure to charge the system up. Because you can see what happens here is, and let's just take a look at the red line on the top first. You know, here I'm condensing here somewhere around 225 pounds of pressure, right? That's my liquid pressure, 225 pounds. And the system's running fine, and as it's running fine, I've got a liquid temperature here somewhere around 180, and a liquid temperature, other side, somewhere around 70 degrees, okay? Scratch that line off there, this is no good. We're somewhere around 80 degrees liquid temp, 70, what is that, 65, 70, 75, 77 degrees or so of liquid temperature, and that resulted in a subcooling somewhere around 18 degrees, right? These are temperature on the right, and these are pressures on the left. So somewhere around 18 degrees. When I block that condenser off, right, I increase the head pressure up to 250, you can see it resulted in a corresponding increase in subcooling. And then I blocked it off again, and it also increased the subcooling again. You're going, oh, wait a minute now. How's that possible? You told me earlier that if the subcooling changed, the superheat would change because we're changing the amount of refrigerant in the coil. Well, I also told you that the coldest the liquid line could get, the coldest it could get, was down to the outdoor ambient temperature. And what's happening here is every single time we're increasing the pressure, we're basically, by blocking the condenser, we're changing the design characteristics of the system. In other words, the pressure is rising faster than the liquid temperature. The liquid temperature, again, you know, here's the highest it got. Whoops, sorry, straight across there. Trying to run this mouse is tricky sometimes. You know, it only went up, from 77, this is 80, 85, 90, it only went up a few degrees. The pressure went way up there. So what happened was the condenser is so oversized on this high efficiency system that the pressure goes way up, but the liquid's still able to maintain a, you know, very reasonable temperature ranges. And what's happening is we're artificially raising the subcooling, okay? So we're raising the saturation pressure without changing the liquid temperature very much, changing the design characteristics of the condenser. So we really weren't, because you can see the superheat remained constant, we weren't changing the level of refrigerant in the coil, we're changing the way the thing operated. The reason I tell you this is some guys will tell you on a mild day, go out and wrap cardboard around the condensing unit and just, you know, raise it up and try and charge it by subcooling. Well, if you do that, you're going to undercharge the unit because you're going to indicate higher subcooling than you actually have. You're going to come back, you're going to think you got a leak because you go, oh, I charged the thing to, you know, 10 degrees of subcooling. When I came back, now it's only 2 degrees of subcooling. Well, it's because you've changed the design characteristics of the condenser. Can't do that. All right. The nice thing, again, when you go back to a digital gauge, you know, one of the things I like to point out here, you know, we got superheat, we got subcooling right on the graph. You can see it's 9.7 degrees of superheat, 13.3 degrees of subcooling. The digital gauges, because they're digital, they can be very precise in their readings, right? Because now it's not interpolating the temperature pressure chart within 5-pound increments. It's calculating it right down to the 1/10 of a psi and the 1/10 of a degree, so we can get a very accurate reading. We can see what's happening and not what happened. Because we're watching superheat and subcooling at the same time, I can see exactly how both sides of the system are operating. And I can tell if there's problems with the system. And if I have a system that's hunting a little bit, I can use the min-mean-max function to see what the minimum superheat was, the maximum superheat was, and then at the end, see what the average is of those readings. So it makes it very handy. You've got to make sure you verify both sides, pressures, temperatures, coil temperature, superheat, and subcooling, because one side will lie about performance. Okay, we can't just go, oh, it's a TXV, I'm going to get the subcooling correct and walk away. You don't know for sure that that TXV is operating properly. It could have a loose bulb. It could have a defect in installation. You've got to check both sides of the system. Same thing with a fixed orifice before we can walk away. Now, the last thing I want to talk a little bit about is temperature split. And we talked a little bit earlier about airflow. And back when I first started in this industry, my dad would tell me, just charge it to the correct superheat, get the target superheat, and then go back in the house and set the airflow by getting the split right. Get about 20-degree drop across the coil. That's good, okay? And split, we typically think about split. What it is it assures that the airflow and the refrigerant charge are proportional. It assures that basically we have the right amount of refrigerant in the system for the airflow that we have. And it verifies proper operation of the coil. It verifies proper relative humidity removal and optimal performance. The thing about evaporator temperature drop at 20 degrees, forget about it, because it's not right. The evaporator temperature drop varies with relative humidity, and that could be anywhere from 16 to 24 degrees with ease. If we look at this, this is a split chart. Again, it's page RD9. You can download this off our site for free. We have a link to it. This shows us what the split should be. So, where did my dad get that from? Well, some engineers sometime told my dad, yeah, about 20-degree drop across the coil, because if the system, again, was designed to operate with a 67-degree return air wet bulb and 80 degrees outdoor air temperature, well, that comes out to about a 18-degree drop across the coil, right? Now, if we're talking 95 degrees, you can see that's increasing if we go out there, so it might be closer to 22 at 95. I just picked 80 on this. But you can see what happens is as the wet bulb goes down, right, as the wet bulb goes down, so if we go from 18.3, which is right here, we're at the center, 18.3. If we drop that wet bulb down to 59, well, now the temperature drop across the evaporator goes from 18 to 23 degrees. And the reason it changes is more energy is going into dropping the temperature now because there's less humidity to deal with. Remember, wet bulb takes into account heat and humidity. So as the humidity drops, so will the temperature drop across the coil will increase, because now as the humidity drops, more energy is going to dropping the temperature than it is removing humidity. As the humidity goes up, you can see here, if we went up to the far end, if we got up to a 76-degree wet bulb, right, we might have an 8.7-degree drop across the evaporator coil. And you go, holy cow, that thing can't be working right. Well, it's working exactly like it should, because the humidity is so high that all the energy in the system is going to convert in that water vapor in the air into water. That's why if you've ever started a system, when it's a new installation and the house hasn't had cooling before, and it's like 80 degrees outside and 80% relative humidity in the house, you'll start the thing up and it'll start running, and you're over there and you're watching the thermostat. The thermostat's not coming down, but the house feels cooler, and you're going, what the heck? It feels cooler in here, but the thermostat's stuck at 80. And, of course, as any good service technician does, you justify in your head going, oh, well, the walls are still hot, and that's why the temperature hasn't changed. Well, it has nothing to do with that. The reason the temperature hasn't changed is because we're removing such massive amounts of humidity from the air that there isn't much energy going to drop in the temperature yet, right? The air feels cooler coming out of the register, but not very much cooler than it is going in. But if you went downstairs and pulled the condensate drain off, you'd find, that you got a quarter-inch stream of water pouring out of the evaporator coil, because all the energy is going to convert it's latent heat energy or hidden heat energy going to convert that water vapor to water. One thing here, I did block out this section of the chart for those of you that are science geeks like I am, right, you can see here at a 70-degree return air dry bulb, the highest the return air wet bulb could be is 70. You can't be at 71 because at 70-degree wet bulb and 70-degree dry bulb, we're at 100% relative humidity. Okay, and I've blocked this section out. So this is, somebody threw this in an Excel spreadsheet somewhere and they extrapolated it out, but in reality, these sections that are blacked out, this is impossible. Right, the wet bulb can never be higher than the dry bulb temperature. And you can see here, well, I don't know why I blocked this section out. I have to go back and look at my notes here, but I just wanted to, or why I had this 19.3 degrees here at 62-degree wet bulb. Oh, this is corresponding to 50% relative humidity at 75 degrees indoor air temperature. So under normal conditions, if the return air dry bulb is 75 and humidity is 50%, this is where that 20-degree drop across the coil came from, about 20-degree drop across the coil came from. All right, so just finish this thing up here. Just, you know, there are some tools we recommend if you get on the phone with me or you get on the, oops, this is not Testo 605H2. This is supposed to be a Testo 316. Oh, geez, Bill, it sold my mind. What is it? 316. 416. I got my dyslexic here. Testo 416. Testo 500 series and manifold or digi-cool. Really recommend you go with a digital manifold because you want to get the higher accuracy to get your target superheat where they need to be. You're going to need something to measure return air wet bulb, and that could be a Testo 605H2 for wet bulb temperature, something to measure airflow, the Testo 416, 417, or an field piece STA2 for airflow. You've got to have something to measure airflow correctly. A video scope is very handy for inspections of the evaporator coil. Typically, you can pull the limit out, fish the video scope up underneath the evaporator coil to see if that coil is dirty. Testo 510 for static pressure, and we do carry some static pressure test kits, and I'm going to take you here in a second and show you where the guides are. I'm going to escape out of here. The slides will be available so when we're done, so if you need a copy of these slides to get this last one, you'll be welcome to it. Do want to show you a couple things online we've been working on before we wrap this thing up. And I apologize, I went over a few minutes on here, but I hope everybody appreciated the content here. Let me escape here. Discard. All right. And a couple things on the site. And I did take some time to put some detailed notes up here. So if you go to AC refrigeration charging and how to charge AC systems, we do have a whole bunch of free download guides here. So, you know, if you click this one here, this is a PDF file. This pulls up that residential charging guide, and here, a couple pages down, are those charging charts that we used in the presentation. So you're welcome to download this when we're done here. There's a troubleshooting guide, an enthalpy chart, how to use the pressure temperature chart as a tool, some guides on airflow and commissioning worksheets, and I've sort of outlined the process here step by step on how to charge a system, how to use the charts, some notes on subcooling that go into a little more detail, a little video here of how to do that process, some notes on the weigh-in method and approach in commissioning the system, verification of capacity, and again, some of the required tools and stuff right there. But this section of the site, if you go into some of these content pages, you'll find there's a lot of great information here on how to properly charge a system. We've done the same thing if you need help with evacuation. We have some stuff on vacuum training here. Spent a lot of time going over this information and how to properly commission the system and how to get the evacuation right. So you'll see some content pages on here. Feel free to visit those when you're done and download the free information if you'd like to do that. But I'm going to go ahead and open up, see if there's any more questions here. And I don't see any on there. So if you have any questions you'd like to get a hold of Bill or I, please feel free to drop us an email. And we'd be glad to answer any other questions you might have. appreciate you coming out for the webinar. If you get a minute and you could actually go back, one thing I would like to show you before I let you go is if you would go to our onto our webinars and leave us a comment here where it says write a review. If you just go to the webinar here section and write a review for us, I would really like some feedback on this particular webinar because it's the first time we've given it. And again, that's just under tips, free webinars and guides. I'd like to know, was the information valuable to you? Was it helpful? Or if there's anything you would like added to it in time. So if you've got anything, I'd appreciate that, that feedback. But otherwise, we are all done for the night. And thank you guys very much for attending and appreciate your business past and future.